Hello there. Hey, this is HDF Data Services. I'm John Readey. Glad you could all make it. My background, I've been a senior architect at the HDF group for about 3 years. Before that, I worked at Amazon AWS. And before that, I used HDF 5 when I was a developer at Intel. So I've kind of gone from the science area to commercial and back again. But that's that. I think a lot of you may have heard of HDF, but haven't used it, or at least not used it directly. What is it? Well, it's a way you can store data, and you can think of it either as a C API, a file format, or a data model, and it's actually all of these things. It's sort of like a file system within a file. So if you have a collection of data, you can keep it all together in a file. And this data can be things like attributes and collections and larger data sets. And it's very convenient to access. Chunking and compression are key features. So with compression, HDF5, you don't need to compress the entire file. You can compress or decompress just the pieces you need as you access them. Okay. So what's so great about this? Native support for multidimensional data. Your metadata is together with your data. It's portable. We support a variety of different operating systems. And you can kind of focus on the logical view while not worrying about kind of the storage system itself. Okay, and the wheel spins. Okay, so there's a lot about HDF5 that I don't have time to cover. I'd refer you to Andrew Collette's talk from SciPy 2015, where he goes into HDF5 in more detail and the Python interfaces to HDF5. So the main focus of this talk will be the Highly Scalable Data Service, HSDS. And what it is HDF5 that is optimized for the cloud. The challenge is that if you just take the regular HDF5 library and run it on a cloud compute instance, it's not really optimal for a variety of reasons. HSDS focuses on using AWS S3 for storage rather than local file systems. This means you have built-in redundancy, it's cost-effective, and you have scalable throughput. And what I mean is that if you have 100 nodes who are accessing content from the same S3 bucket, you have tremendous throughput in terms of megabytes per second. The service itself runs as a cluster of Docker containers. So these can either be on one machine or they can be on a cluster of machines. AWS supports ECS, which is basically Docker that runs across a cluster. The service itself is feature compatible with the HDF5 library. And it's implemented in Python. And async I/O is a key aspect of it. And we'll kind of cover that in more detail later. So how do you interact with this thing, right? Well, you basically, the fundamental interface is the REST API. SDKs provide a language-specific interface. So for this crowd, H5PyD is the Python SDK for the HSDS service. There's no limit to how much data you could have in the service. That's one good aspect of the S3 storage. You can have multiple clients can be reading and writing from the same data source. Okay, that's a feature that's not part of the standard HDF5 library. And the performance, as the name entails, is scalable. We cache recently accessed data in RAM. Requests are parallelized across multiple nodes. And I'll illustrate how that works later. If you add more nodes to your cluster, you'll get better performance. So kind of describing high level the client-server architecture, you have the service on the right, and think of it as a black box. All you need to know about it is that it supports the REST API. We can have, say, a web-based client that's using Ajax, JavaScript to interact with the service. We can have a H5PyD, which are Python SDK, and Python applications using H5PyD. And there are a set of command line tools that also use H5PyD. In progress is what's called a RESTful. So vol is like a plugin for the HDF library. Basically, it substitutes a different backend to the library. And this will enable C and Fortran applications to use the HDF service without any change in their source code. So this brings us to the question of how do you store HDF content in S3? There's some kind of goals here. We want to limit the object size. We want to support parallelism for read and write. We only want the data that's modified to be updated. And we want to support multiple clients reading and writing to the same file. I had to use the air quotes for that. So what we came up with is the idea that we're going to take what is normally a single file, a single POSIX HDF file, break that up into potentially millions of S3 objects, and we store those objects in the S3 bucket. So in this graph here, you can imagine this as a data set. So chunking is this concept in HDF where we take a data set and we partition it into regular sized blocks. So in HSDS, each of these blocks is stored as a separate S3 object. And so, for example, if I wanted to read this yellow region in the middle, the service will say, okay, well, this region crosses 6 chunks. Those 6 chunks are stored as 6 S3 objects, and it'll do all the dirty work of finding those objects and extracting the data that's needed, putting them together, and sending that response to the client. In more detail, there are actually 2 layers of nodes in the service itself. We have the service nodes, and they are the front-end interface to the client. And then there's back-end nodes called data nodes. So one challenge of S3 is that it's not read-write consistent. So if you write to S3 and read back right away, you may not get back what you just wrote. We would rather provide a read-write consistent service, so we kind of enable that on top of the underlying S3 system. And how we do this is that we have the data nodes, and they effectively partition the bucket. So for each data node, there's one partition of the S3 bucket. And so any particular chunk belongs in a partition, and it's the responsibility of a particular data node. Okay, so if you think about the write-read case, right? We write to a data node, it updates its local content, flushes through S3, and then when the read happens, it can refer to its local instance, not go back to S3 again. Okay, so how requests come in? So I mentioned that, let's say we're doing that hyperslab selection over here. That request would come from the client, go through a load balancer, land on one of the service nodes. The service node would deterministically know which data nodes are needed to service that given request. It would multiplex a bunch of requests to the different data nodes. Each of these data nodes in parallel would be reading from S3, decompressing the data, segmenting the data it needs to the service node. Those responses go back to the service node. Service node puts it all together and sends a response back to the client. So I mentioned async I/O. Async I/O is great for any kind of I/O-bound service. So rather than, say, using a bunch of threads or processes, with async I/O, you can have one process and use what's called like task-level parallelism. So if I say I have a function, and I can do a regular call, just like I do, and let's say I want to do a call that's going to block on I/O. So I say await, a blocking call. Right then, the process can switch to a different task. So it's not blocked waiting for the response to that I/O. And this is really useful if you think about the different levels of I/O latency we have. Service node needs to talk to data nodes. Data nodes need to talk to S3. using async I/O, we can get a lot of work done with just one process per node. Here's an example of using parallelism. Here I have a list of chunks. And I create a task for each chunk. And I call await async.gather. So this will send those requests out, okay, in this case from service node to data nodes. Each of those data nodes will be processing stuff. And I don't need to think about it as a service node until I come back from this await call. Right? And so in the meantime, the service node can be doing other useful work while the data nodes are doing their stuff. So all in all, I think it's a very efficient and fairly easy to program way of doing things. Also, I'd like to mention Docker. If you've ever developed a clustered application, it's really, really hard. Docker makes it 1,000 times easier. So with Docker, I can simulate a cluster in my notebook by having a bunch of containers running. They all do their things. As far as the container goes, it's just like it was a separate instance in AWS. And so I can debug things, get features working, and then boot it up to AWS. And 9 times out of 10, it just works as designed on my desktop. Async I/O depends on having packages that support async I/O. So in our case, AAO HTTP is an async HTTP client server, and AAO Bottle Core is an async package for talking to S3. So that's oftentimes the biggest challenge of using async I/O is that you depend on packages that support async I/O in turn. And also, I want to mention NumPy. NumPy is very heavily used within the service, and it's also used within the H5PyD client. So you think of like HDF5 as the storage mechanism, and the typical pattern is that you read chunks of data from HDF5 data sets into NumPy arrays, process something that's reasonably fits in the memory, and then move on to the next piece of data. Oh, and also I want to mention H5Py. Basically, how I implemented H5PyD is I took the H5Py code and I stripped out all the stuff talking to library, replaced that with a bunch of REST calls, and hence we have H5PyD, which has the same client interface as H5Py. What I want to do is provide something that's compatible, so you can have existing Python applications using H5Py, and then they can, you just change the import to H5PyD, and these should work with the server. And it's also compatible with H5Serve, which was the reference implementation to the REST API. I've added a few extensions to the H5Py interface for features that are part of HSDS, but not part of the H5 library. For example, listing content folders. So on a regular file system, you would do ls, or the equivalent Python interface, to list content in a directory. But you don't have that with a server because you don't have direct access to these files. So there's a folder object, and you list content in folders. Similarly, there's no chmod for content on the server. So we have a system called ACLs that can use to enable who can modify or read content on the server. And while it was added, I added a PyTables-like query interface, and I'll done with that in a bit. The command line interface is a set of simple tools that you can run a shell to do things like list content, upload files, download files, and so on. Okay, so let's do some demos. Recently, we've been working with the National Renewable Energy Laboratory. Okay, thankfully, they're still in business. They spent a lot of time creating a simulation of wind over the continental US. And it's a 50 terabyte collection of data files in HDF5. And their challenge is they wanted people to be able to access this data set. And they came to us to utilize HSDS because this will enable people to access that data without downloading the entire 50 terabytes of data, which would, as you can imagine, be kind of impractical for most people. And I actually have their data here in the demo, and you can see how that works. So let me switch. So that's first. I'm going to make this larger. So I mentioned the command line tools. What? My internet connection died. This one challenge with the server is that you're kind of dependent on the internet to work. So here we go. So can you guys read that? So HSInfo just tells you what you're connected to, the server status, who you are. I get confused sometimes. Server version and uptime, so on. So I mentioned HSList. So I can do this. So HSList/home/John shows me there's a folder and two files, basically. So a couple things to note. /home/John isn't a folder on my desktop. I don't have this mounted as a drive. It's just some virtual folder that exists on the server. The other thing to bear in mind is that this content is universally accessible. So any machine running anywhere in the world, as long as it has an internet connection, can run the same command and get the same result. Right? So this can be very useful in the context of saying you have notebooks running in Docker containers that don't have access to a local file system. That same content can be accessed from anywhere. So this is a list of files, and if I show one file, we will see the HDF5 content in that file. So there's a group, there's a subgroup, there's a subgroup, there's data sets, there's links, soft links, et cetera. And if I do if I change the log level, I can see the actual HTTP requests that are coming in and out. So displaying this content here actually devolved into a set of HTTP requests. I went from my desktop to one of those SN nodes, from the SN nodes to one or more of the data nodes, from the data nodes to the S3 bucket, then back to the data nodes, back to the service node, back down to my desktop. And the show ACL will show you the ACLs. So here I added the show ACLs option, and it says there are 3 ACLs. There's this default, which is read-only, which means any one of you can do this and see the content. John is for me, and it says I can do anything: create, read, update, delete, read ACL, modify ACL, and this test user. Now, I mentioned the National Renewable Energy Laboratory, and if I look at this folder called NREL, I can see their content. And if I add some more flags, oops. we can see we have one file, and I use air quotes again, right? It's not really a file. It's 5.6 terabytes in size. Okay, so let me switch to a Python notebook. Okay, and I guess we should make it larger. How's that? Okay, so we do an import h5pyd, and now we're going to open the file. So that same path, nrel/win-us.h5. And there. Okay, so I've opened this 5.6 terabyte file. Cool. And now there's an attribute. Okay, so I mentioned that HDF is nice in that you can have these metadata tags that you can associate with content to describe content or such. And one of these is called history. And it says produced by 3-tier Inc. under NREL subcontract. Okay, good to know. So what I've done is I reached into this file and I pulled out one particular attribute and displayed it in my notebook. If I do list, we'll see all the data sets in this file. So let's pull out one particular data set. And one difference between h5py is that if I do dset.id.id, in h5py, you'll get a numeric ID, and here we get a UUID, right? So this is the way to identify that particular data set. So the shape is 8760 by 1602 by 2976. So the 1602, 2976, they're a kind of grid over the geographic region of the continental US. And the A760 is a bunch of time slices, right? 1 year of data, 1 hour per slice. So by slicing into this data cube, different places, we can see the values at different hours throughout a year. So h5pyd owes a lot to NumPy, and there's a lot of similarities. There's enough differences to trip you up now and then. But like D-type, this looks like a regular NumPy D-type. It's a float 32. And chunks. So this larger data set is broken up into these chunks. Each chunk is 32 by 50 by 186. So I think it's like 2 megabytes per chunk. The entire data set is 155 gigabytes. And one slice of that data set is, right down here. Oh, this is the, I'm calculating the number of chunks. So this one data set has 140,335 chunks. So that means this data set's comprised of these 140,000 S3 objects that are being stored. And each slice is around 18 megabytes. So imagine we slice this data cube, you're across a bunch of chunks, and that comprises the data for that slice. Okay, so now we're going to read a slice at the hour 1898 out of this data cube. And I use this NumPy syntax of : :8 to say, don't return every value from that slice, return every 8th value. And that took 3.27 seconds. And if I do it again, I bet it's faster, or not. So once the data nodes read chunks in, they'll stay in memory until they get pushed out because of new requests. So accessing data that's been recently referenced is faster. If we change the time slice by 1, it'll still be relatively fast, 2.3 seconds. But if I change it by a lot, it's going to be slower. Because now I'm accessing data that apparently isn't resident in the memory of the data nodes. So it has to go to S3, read the values out again. And let's show the data. Okay. So we can, if you squint, you kind of recognize the continental US here. Maybe not. Okay. All right. Anyway, so now let's zoom in to a smaller region and show a full res piece of that. Okay, so 2 seconds, and another plot. And now we're seeing some zoomed in part of the continental US for the wind velocities. Okay, so now we're going to instead of extracting a geographic data from at one time, we're going to extract all the time values for one geographic point. Okay, and now this can be challenging because as you do the time series access, you cross many, many chunks. But this is not so bad. And I should say, I'm actually running this just on a single EC2 instance. We haven't gotten to the point of yet running this over, say, hundreds of instances, but it should be much faster as you scale up the physical hardware. So because the data nodes can access these chunks in parallel, it's much faster than accessing serially with the HDF library in many cases. Okay, so there's 8,760 points selected, and we do a plot, and we see this is basically giving you the variation wind over the entire year at that point. Okay, now let me switch to another notebook. I just want to show the query interface that I copied from PyTables. So here I'm going to open a file called S&P 500. It has stock quote data since 1970, I think. So just one data set. There's the D type. And the shape is about 3.2 million rows in this data set. Again, we have a chunk for that. And if I just show some values, it looks like this. Okay, and then I can do, get through out of time. I can do a read where symbol equals APL, and I'll see the values for Apple. Or maybe not. Okay, so that's about it. Any questions?